Okay, this is lesson 104, and we're going to talk about writing repeating decimals as fractions. So first of all, let's just remember the number systems that you have learned so far in your mathematical career. Most of the time you have been working with real numbers. That's all the stuff in the green circles. Recently, you learned about the complex numbers, which include the imaginary numbers and all of the numbers that have a real part and an imaginary part. The real numbers and the imaginary numbers are part of that set. The numbers in this green oval can be broken up into two completely disjoint sets. Okay, disjoint means they have no members in common. Those two sets are the rational numbers on the right side and the irrational numbers on the left side of that line. What is a rational number? What makes a number rational? Well, there's a definition for rational number. A rational number can be written as a fraction with integral numerator and denominator. So rational refers to a ratio, and a ratio is usually represented as a fraction. So that's why they're called rational numbers, because they're the numbers, all the numbers that can be represented by a fraction with integral numerator and denominator. And all that means is that the numerator is an integer and the denominator is an integer. So you can see that these numbers from the rational side are all numbers that can be written as fractions with an integer in the numerator and an integer in the denominator. So for whole numbers or integers, you can just put a 1 in the denominator and it is rational. You can just show that, yeah, it's rational. It can be written as a fraction. Okay, so if written as a decimal, so if you took a rational number and you wrote it as a decimal, then that rational number will either terminate, meaning it will end, or the decimal will repeat in a pattern. If the decimal does not terminate or repeat in a pattern, that number must be irrational. What we want to do is show that this decimal right here, 0.00314, is a rational number by writing it as a fraction with an integer in the numerator and an integer in the denominator. And that's pretty easy to do if you remember your place value system. If you have that number 0.00314, all you need to do is remember that to the right of the decimal place, you have your tenths, hundredths, thousandths, 10,000ths, 100,000ths, and it just keeps going by powers of 10. So those are the negative powers of 10 to the right of the decimal, 10 to the negative 1, 10 to the negative 2, 10 to the negative 3, 10 to the negative 4, and 10 to the negative 5. So since this goes to the 100,000ths, I can write this as the fraction 314 over 100,000. So I did it. I showed that this is a rational number. It can be written as a fraction with an integer in the numerator and an integer in the denominator. Okay, show that 0.0000623 is a rational number by writing it as a fraction of integers. So when you start having all these zeros and it's just, hard to think about the place value, there's an easy way to figure out what your denominator is going to be, and that's just to count the digits to the right of the decimal place, 1, 2, 3, 4, 5, 6, 7, 8, and just for your denominator, just write 1 with 8 zeros, 1, 2, 3, 4, 5, 6, 7, 8, and put your commas in there, and then just write 623 on top, and that fraction does equal that number. Okay, so example 104.3 says show that 0.01623 with a line over it is a rational number by writing it as a fraction of integers. Now that line over the 2,3 means that 2,3 repeats, and it just repeats forever. So this decimal does not terminate, but it does repeat in a pattern. So we know that it represents a rational number. It can be written as an integral fraction. But how do I do that? Because the 2 and the 3 just repeat forever. How am I going to figure this out? So there's a mathematical trick that we're going to use that gets used in a lot of different proofs and derivations. And I'll show you how we do it. So what we're going to do first is we're going to call this number n, and we're going to write out a few repeats of the repeating part. So we'll write it out. N equals 0.01623232323. Write it out a few times. I'm also going to write 100n. I chose 100 because the 2 and the 3, there's 2 repeating digits, and 100 has 2 zeros. So what I'm going to do now is I'm going to line up the decimal points and subtract n from 100n. We didn't do anything crazy. We just wrote n and we wrote 100n. And now what we're going to do is subtract those two equations. And to do that, we had to scoot the top part over so that the decimal points line up, because you know when you subtract decimals, you have to line up the decimal points. Now I'm going to put in some vertical lines just so we can keep things organized and you can see what's happening here. You can see that since I lined it up this way, all the 2 3s are going to cancel. When I subtract 2 3 from 2 3, I get 0. So all the 2 3s to infinity are going to cancel out. And I'm just left with this 1.623 minus 0.016. And so that's the subtraction I'm going to do. And I'll get 99n, because I'm subtracting 100n minus n, is equal to 13 minus 6 is 7, 1 minus 1 is 0, 6 minus 0 is 6, and the 1 is still there. So I'm going to have 1.607 is equal to 99n. Then I'm going to divide both sides by 99. I'm going to get that n is equal to 1.607 over 99. I'm almost there. Now I have written n as a fraction. And the n, remember, is the number I'm talking about here that I want to write as a fraction. So I'm almost done. I have written it as a fraction, but it doesn't have an integer in the numerator. So all I need to do is use the rule that says I can multiply the numerator and the denominator of a fraction by any number besides 0, and that will move that decimal 3 to the right, and I'll have 1607 over 99,000. And that is a integral fraction that equals 0.01623232323 and so on. And you can see if you punch that decimal into the calculator, hit 1607 divided by 99,000, it does actually equal 0.01623 repeating. So we have proven that that 0.016232323 repeating is rational. It can be written as a fraction. Okay, we want to show that 1.031543543, 543, and so on is rational. We're going to do the same kind of thing. We're going to write n, 1.0031543, 543, and so on. This time we're going to multiply n by 1,000 because we have 3 repeating digits. So 1,000n is equal to 1,003.154354354, and so on. All right, we're going to scoot everything over so that the decimals line up, and we're going to subtract n from 1,000 to n. So move that over and put some lines just to make sure everything lines up. And now we'll do the subtraction. 3 minus 1 is 2. 4 minus 3 is 1. 5, 1, decimal points, 2, 2 zeros, and a 1. Now we divide both sides by 999, and we will get that n is equal to 1002.1512 over 999. And we're almost done. We have almost written this as an integral fraction, but this time we're going to have to multiply the top and the bottom by 10,000 so that we can get that decimal point on top moved all the way to the right. So it is an integer now. And on the bottom, we're going to have 9,990,000. Now, you may notice that the fraction is not reduced. It's got an even numerator and an even denominator. So if this fraction was the answer to a question that had a fractional answer, then you would want to reduce that. But that's not what this problem is about. It's not about finding a value. This is a problem about showing that that decimal right there is a rational number. Once you have written it as an integral fraction, you have proven that it's rational.